Okay, I think we are ready to start. So welcome everybody to the first second evening meeting of the year. This is an online meeting only. The structure of the meeting will be as usual. We are having our speaker for tonight delivering her presentation, and that is going to be followed by a Q&A session. You should be able to find the chat box in your screen where you can submit questions at any time during the presentation. And at the end of the presentation, I will be reading your questions. Today, we have the pleasure of welcoming Holly Williams. She's a senior environmental engineer at SRK Consulting. She has over 10 years experience and specializes in the application of data science and statistical approaches to incorporate risk and uncertainties into mine waste studies and designs. Holly has an undergraduate degree in civil engineering and a master's degree in data sciences. Her experience includes the design of tailing facility designs, dam break assessments, water balance studies, mine reclamation and closure. She has been involved in several projects, not only in Canada, where she's based, but also in the US, Mexico, Australia, South America, Europe, Russia, and Africa. Last year, her paper titled Incorporating Inherent Uncertainties in Seismic Liquefaction Assessment, that is the title of today's presentation, and which was published in the Geotechnical Engineering section of the Proceedings of the Institution of Civil Engineers, was awarded the 2023 TKC Prize. This award, the TKC Prize, is given to the best paper published by the ICE in the field of structural and soil vibration caused by mechanical plant, winds, waves, or seismic effects. And nominations for this award are coming from SECER, this award that is given every year. Today, Holly will be talking to us about her TKC winning paper. So, Holly, welcome to SECER, and please go ahead with your presentation.
Thank you. Let me just switch to sharing my screen. Oh, I think it won't let me until you stop sharing yours. There we go. Perfect. Okay, so Guillermo, just checking that my screen's being shared now.
I can see that.
Perfect, thanks. So, you know, before I get into this presentation, I just want to start by thanking you, Guillermo, and SECER for inviting me to give this presentation today, and also to the Institution of Civil Engineers for co-hosting. For someone like me, it's just really exciting to get an opportunity to share this paper, and especially to a broad audience like this. And I also just wanted to take a quick minute to acknowledge my colleagues at SRK. Many of them acted as sounding boards while working on the paper. And in particular, Daryl Hockley, he encouraged the idea in the first place, and provided a great deal of support, both technical and editorial, in the preparation of that paper. So I think we all have to deal with uncertainty in our day-to-day work. And from a very quick search of recent seismic engineering papers, some of which are shown here on this slide, it seems to me like there's a lot of interesting work happening specifically to deal with uncertainties in this field which you work, and also seem to be a key topic in a recent Mallet Milne lecture. In this presentation, though, I'm going to talk to you about a source of uncertainty that I think seems to get a lot less attention than the other types. And in the title, I refer to it as the inherent uncertainty, but throughout this talk, I'm going to call it the transformation model uncertainty. And I'll describe what I mean by that a little bit more detailed later in the presentation. But I think the key point for now is that it's the process that gets us from raw data to a material property. And this talk focuses specifically how to quantify this uncertainty and its use to make decisions about seismic liquefaction stability of tailings facilities. And I recognize that, this specific example may not be something that you do as part of your work, but this type of uncertainty is present every time we estimate an input or derive a parameter using empirical correlations. So, by the end, I expect you'll be very familiar with the implications for the specific example that I talk about. But more importantly, I really hope that it generates some ideas about where there might be parallels in your own practice and how it could relate to your work and what you do. So before I get into the paper details, I do recognize that this is a diverse crowd, and there's some of you who may be bona fide experts in liquefaction and tailings engineering, but I also recognize that there could be others who might not have direct experience in these areas. So to make this presentation accessible to a broad audience, I thought I'd start with some quick definitions of key terms that you need to know. Next, I'll go into the details of the paper, which are around that specific example I referred to. The paper includes an example hypothetical case study, but in the third part of this presentation, I'll show you a real world application. And then we'll finish with summary and conclusions. So these are the three things that I thought would be worth defining for this talk. Starting with tailings and tailings storage facilities. So, all of us rely on mining to sustain our everyday lives, right? In order to get metals and minerals that we need to make computers, smartphones, solar panels, etc., we need to extract them from the earth. So whatever the metal or mineral is that we're interested in this case, it's indicated by those cartoonish yellow specks. We first need to dig it up out of the ground. Then we have to process it to extract the thing that we're interested in and send it off for use in products. But, as you can see, those yellow specks were only a small portion of what we dug up. And all that residual soil and water that's left over is what we call tailings. And what we usually do is place them in purpose-built storage facilities. And those facilities usually include large earthen embankments to contain that residual tailings and water. And I know this is quite cartoonish, but here's some examples of what these facilities can look like in real life. And compared to other structures that need to be engineered seismically, some of the key differentiators or challenges with tailings facilities are that we actually build the structural dams out of earthen materials instead of manufactured ones. The stored tailings have high spatial and temporal variability. And the facilities themselves are never finished. They're usually continuously being constructed, raised, modified throughout their operation. Okay, next is liquefaction. And given that this group has a focus on seismic engineering, I imagine all of you are already quite familiar with the effects of liquefaction. And some of you will also be experts in the technical mechanisms, but so I'll just do a very quick overview. So here, another simple cartoony schematic of what happens to soil or tailings particles during an earthquake. On the left is a drain scenario, and on the right, an undrained scenario. For simplicity, I'm sort of showing the void spaces as being empty in the left scenario and filled with water in the right scenario. But technically, there still could be pore water present in the left scenario, but the key difference is that that pore water can't escape under the drain conditions, it can escape under the drain conditions, but the pore space is filled with water in the undrained scenario can't escape. So in both these cases, more contact between particles, which is indicated with those brown arrows, means more friction and higher strength. And then, so now let's look what happens during earthquake shaking, starting with the drain scenario. So when we shake, loose particles want to densify into a tighter configuration. the void spaces are reduced and there's more contact between particles and some overall settlement. But now on the right, the undrained scenario where we have those pore spaces filled with water with nowhere to go, during earthquake shaking in this case, the particles again want to sort of move down and densify, but water is incompressible. So what happens is the blue arrows represent the pore water pressure, which increases. And when this excess pore pressure starts to exceed the frictional forces that keep the particles together, those particles get forced apart. So particle to particle contact and friction reduces, and then you end up getting something that starts to behave more like a fluid than a solid. And I think, as you know, when soil that's below or within key structures starts to act more like a fluid, it can have some extreme consequences. So here's just some photos of liquefaction damage observed after earthquakes. And I imagine you'll be quite familiar with some of these already. But there are also some recent cases of flow liquefaction failures of tailings facilities that have led to devastating consequences. So I'm going to play a video of the 2019 Feijão tailings facility failure. And just to note, this tailings facility doesn't really look like the ones I showed you earlier. And that's because it had actually been inactive for a number of years and was covered and vegetated. Another thing to note here is that the liquefaction here wasn't actually seismically triggered, but it is just quite a unique case because we captured the onset of liquefaction on camera. So let me just press play here. So as you can see, this was a particularly terrifying example in the industry, especially because of how fast it occurred. So I think you can see why we're so concerned about this particular failure mechanism. And then lastly, some of the most common approaches to assess liquefaction potential in tailings are based on cone penetration testing or CPT. And the CPT is a long metal probe. We start pushing the probe at a constant speed. And as it's being pushed, it collects continuous readings of three things. So there you see the red that's disappeared is the resistance that's being felt at the end of the rod, the green, then the friction against the sides of the rod, and that blue U is the horizontal pore pressure. And when we look at the combination of all these three things, it gives us indications of what types of material we might be in. Sorry, that video seemed to glitch. I'll see if it keeps going here. Right. Yeah, so you can see how the combination of those three parameters gives us indications of when we're in different types of material. And we can use it to make inferences about its expected behavior. But something to keep in mind is that it does not directly measure the key parameters that we're interested in. So like when we were talking about liquefaction, that might be something like the actual in situ state of the soil or how loose it is. So instead, what we need to do is rely on a bunch of empirical, a combination of empirical equations and theory to get the parameters that we're interested in. So those are all the definitions, and now we can get into the key idea of the paper. So for seismic liquefaction assessments for tailings, there are generally two steps. First, you do a triggering analysis to answer the question, which is really, will the material liquefy? And then once you do that, then you run stability assessments using liquefied residual strengths in zones that you said were potentially liquefiable. and then verify whether the stability is acceptable. And then the results of both steps are typically presented as deterministic factors of safety. And another thing to note is I recognize some people choose to vary these steps a little bit. So some people might skip ahead and do step 2 first to verify whether liquefaction is an issue before they even start to think about the triggering. Others include some additional steps or slight variants, but even with those variants, there are still 2 points in the process where you need to apply engineering judgment to select, what is the cutoff factor of safety value. We do have current best practice guidance that give recommendations for factor of safety cutoffs for post-seismic stability. And those are typically around 1.1 to 1.2. But there isn't really established clear guidance on what cutoff factor of safety to use for the triggering of liquefaction. As I'm sure you all know, one limitation of these types of deterministic factor of safety-based approaches is that they ignore the effect that uncertainty can have on our estimated probabilities of failure. So I'm sure you've seen something like this before. Factor of safety obviously is proportional to the difference between the load imposed on a system and its ability or capacity to resist it. And the width of the curves in this figure represents the uncertainty. And that overlapping area shaded in red is proportional to the probability of failure. So if we look at another scenario in blue, we could calculate the same factor of safety, but have much narrower uncertainty. And then here for the blue lines, the estimated probability of failure will be much lower, which illustrates that the same factor of safety does not equate to the same level of risk. And then here, what about another case where here the red scenario will calculate a higher factor of safety, but has much more uncertainty and a relatively higher probability of failure compared to the blue scenario, which happens to have a slightly lower factor of safety. So I think this goes one step further and indicates that a higher factor of safety is not always indicative of a safer facility. So there are a number of different sources that can contribute to the width of those uncertainty bands that I just showed. First of all, the soil or tailings that we're interested in has variability. It's never perfectly homogeneous. Then there's error associated with the in situ testing method, as well as the level of site investigation and number of samples that we have, and scatter or variability in the information that we do collect. And then, as we mentioned before, in situ testing, like CBTs, doesn't directly measure the parameters or inputs we need for our models. And instead, we need a transformation model to convert those in situ measurements to design inputs. So it's pretty common to combine all of these types of uncertainties and call it the uncertainty of the measured property. And these are things that will vary site by site and will likely have opportunities to be reduced, either through additional investigations or improved measurement methods. But the transformation model uncertainty is something that is constant and irreducible when you use these methods. I think, in my experience anyway, I think I see that a lot of people relate uncertainties in strength properties that they use in their models to variations in the measurements that they collected. But we sort of rarely see people accounting for the transformation model uncertainty, despite the fact that it can be just as significant, if not more so, especially when we're using models that rely on multiple empirical correlations. So that really was the focus of this work, to show how this type of often ignored transformation model uncertainty is really important to engineers who are making decisions about liquefaction stability. So again, I mentioned that these were the 2 key steps in liquefaction assessments, and they each have different sources of uncertainty. So for the factor of safety against liquefaction triggering, it's most common to calculate it as the ratio of cyclic resistance, or CRR, to cyclic stress, CSR. And then, if liquefaction is triggered, then the post-liquefaction stability will depend mostly on the liquefied residual shear strengths that are estimated. It's very common for these to be calculated using empirical methods based on CPT. So in that case, the measured properties are the CPT readings, and then our cyclic stress ratio, or CSR, also depends on earthquake characteristics. And then there's a number of intermediate calculations, each with their own transformation model to get to those values that we're interested in. And I know that there's a lot of information on here, and it looks a bit like spaghetti, but that's actually kind of the point. This slide is just intended to give you an idea of how many intermediate calculations there are. So in this paper and talk, I'm using the Idris and Bollinger framework as an example, just because it's one of the most widely used. You should note that there are others as well. They vary slightly, but they all have a similar framework overall. And the key to all those empirical frameworks is that they look at historical case histories where they have known seismic events or estimated CSR values. They have CPT data, and then they have observations of whether or not liquefaction occurred. So then what they do is they draw a line or estimate a CRR relationship as a line that best separates liquefied from non-liquefied case histories. And so when we use this type of approach to assess liquefaction triggering potential, we have three main sources of uncertainty. And that is the uncertainty in the estimated CSR value, or the seismic load, the uncertainty in the corrected CPT tip resistance measurements, and the uncertainty in the CRR transformation model itself. And another thing to note is the black line that I'm showing here, it sort of represents the best estimate curve that passes through the middle of the database. So this would be equivalent to, if you're on that line, it means you have a 50% chance of liquefaction. But Idris and Bollinger actually recommend a more conservative curve when you're doing deterministic assessments, and that's what people use in practice. And that curve is effectively shifting this line down and making it equivalent to a 15% chance of liquefaction instead of a 50% chance. And as a quick aside, I mentioned that there's other frameworks. Other authors have adopted different recommendations. So one of the other most widely used methods is Robertson's method, and his recommended deterministic relationship is actually equivalent to a 35% curve, which would fall in between these two lines. Okay, so now let's look at the transformation model for the second step. And because it's sometimes difficult to extract and test undisturbed samples, empirical CPT procedures are also widely used to estimate liquefied residual shear strengths. Here, I'm showing Olson and Stark's method, but again, there are others. But the key is that most methods actually use the same database of about 33 case histories. And those case histories aren't super well documented and do require a great deal of judgment to develop correlations to be able to link CPT measurements to back calculated liquefied shear strengths. So I'm showing Olson and Stark's method, but all methods have the same two key uncertainties, which are the CPT resistance is also a key uncertainty here, and the strength transformation model. So the key idea of the paper was that since we know the uncertainty in the transformation models and the other measured properties, we can just do a bit of math and then calculate how those uncertainties translate to any factors of safety that we estimate using those methods. And then once we know the uncertainty associated with the factor of safety, we can calculate the probability of failure, which is just the probability of the factor of safety being below 1, which can actually make us help us with making more risk-informed decisions. The math and the derivations themselves are shown in the paper, so I won't go through them here, but I do want to highlight the key points you need to know to apply them. And yeah, I know it's a risk putting equations on slides, but I just want to show you what they actually look like, and to show you that with these equations, we can calculate the probability of liquefaction triggering based on any estimated factor of safety against liquefaction. You just need to know that it requires 4 inputs. So first, the estimated factor of safety against liquefaction. And then the other part of this equation is the total uncertainty associated with this estimate. And we calculate that using the second equation, which features the remaining 3 inputs. And those are the variability in the measured CPT resistance, the uncertainty in the estimated CSR or seismic hazard, and the uncertainty in the CRR transformation model, which, if we use Idris and Bollinger's method, is actually a known constant value of 0.2. Using those equations, I can actually plot this graph, and it shows the probability of liquefaction triggering associated with any estimated factor of safety. One thing to note, though, is that the graph I'm showing here only considers the CRR transformation model uncertainty. Or I guess in other words, it ignores the CPT and CSR uncertainties because those will vary site by site. And this curve that I'm showing here also represents the deterministic relationship that's recommended by Idris and Bollinger, and the one that we most often use in practice. And, like I said before, it incorporates some conservatism, so is equivalent to a 15th percentile curve. And I put this dashed line on top to show a comparison to what the 50th percentile curve would look like, or the curve that actually gets drawn through the middle of the database. And, one thing that's interesting for engineers using these results is that you could look at the dashed line, and that illustrates the true uncertainty in the transformation model. And then the solid line is the uncertainty that remains even when we use a very conservative interpretation. And remember, the key point of estimating this factor of safety is to help us identify zones of potentially liquefiable material. So, if the factor of safety is less than 1, I think it's pretty clear that the material has a high potential to liquefy. But when you get values that are close to 1, that's where we really need to apply some judgment. And earlier I mentioned that in practice, it's really common to assume that materials with factor of safety less than about 1.1 or 1.2 are potentially liquefiable. But with these curves now, we can quantify the implications of those different assumptions. So looking at the dashed line, when only considering the CRR transformation model uncertainty, the decision to use a cutoff factor of safety of 1.2 instead of 1.1 is basically equivalent to reducing the liquefaction triggering probability from 35% to 21%, or from about 8.4 to 3.5% when you use the recommended deterministic relationship. So I think this kind of information is actually very relevant to engineers who need to make judgments on which zones are potentially liquefiable. We can also apply a similar process to the second step, where we're interested in estimating the post-liquefaction stability. And now in this case, we have 2 equations with 5 key inputs. So again, the estimated factor of safety, the estimated residual liquefied strength ratio that we use, the variability in the measured CPT tip resistance, the uncertainty in the transformation model used to estimate those residual liquefied strengths, which in this example, when we use Olson and Stark, is a known and constant 0.3. And then the proportion of resisting force contributed by liquefied materials. This is because we need to account for the fact that, some of the area that's going to be part of the global failure surface is from materials that aren't liquefiable. So there's not just a direct linear relationship between the liquefied strength ratio that you use and factor of safety. It depends on what proportion is actually from liquefiable materials. So now, because we have more variables to consider here, we have families of plots instead of one relationship. So on the left, it shows a family of curves for lowered liquefied strength ratio estimates of 0.05. And then on the right shows an example family for a higher liquefied strength ratio estimate. The colors on both curves represent different proportions of liquefiable materials, with blue being the lowest at 25%, then green, then orange, then red. And what I'll do is just maybe highlight a few things that stick out here. So first, and pretty intuitively, probabilities of failure are higher when liquefied materials are responsible for larger portions of the overall strength. Also comparing the left chart, which uses lower strength ratios compared to the right chart, we see that we get higher probabilities of failure, even when we use the same proportion and factor of safety. But one of the most interesting observations, to me at least, is the relatively high probabilities of failure that are associated with a factor of safety of 1.1. Which is the typical value recommended by some dam regulators like the CDA. So, and this really shows me that the use of a constant factor of safety cutoff does not necessarily represent the true risks. So now that we have all these equations, I'm going to walk through an example case study just to illustrate how they can be used to inform design decisions. So this is a picture of one of the real tailings facilities I showed earlier. So imagine we now cut a cross section through this dashed black line. And we have three different geometries or scenarios that cross section might represent. In all of these, the yellow portion represents material that could be susceptible to liquefaction. And the green represents material that isn't susceptible. So usually a starter embankment or outer shell. In this case, in this illustrative case, all three of these examples had a factor of safety of 1 for liquefaction triggering, and then a factor of safety of 1.1 for post-liquefaction stability. It was also assumed that for this example, they all have the same degree of base knowledge or uncertainties, and they all have potential to reduce those uncertainties through additional investigations or lab testing. But the case studies differ in their geometry, in the proportions of liquefiable material, and in the residual liquefied strength ratio estimates. And just as a reminder, again, these are the four key uncertainties. So the CPT tip resistance or variability in the tip resistance. And it's assumed that this uncertainty could be reduced through additional CPT investigations and or calibration index testing. Then the seismic hazard or CSR uncertainty, which can be reduced by performing rigorous site-specific hazard assessments and including strong ground motion stations directly at the site. The uncertainty in the CRR transformation model, which is actually fixed and can't be reduced. And then finally, the uncertainty in the CPT-based liquefied strength transformation model, which can be reduced by performing laboratory testing rather than relying purely on the empirical CPT relationships. So here's, I'm going to show you results for all three scenarios. And as I do for simplicity, I'm just going to show the combined probability of both events. So both liquefaction being triggered and then having a liquefaction slope failure due to insufficient strengths. So in the gray right now, I'm showing the base case probabilities of failure for all three scenarios. And you can clearly see that we get a range of results, despite them all having the same factors of safety. We can look a bit closer and actually break down the contributions of the different types of uncertainties. So this red portion represents how much is due to the transformation model uncertainty, and the blue portion, the measured property uncertainty. Now we can look at what happens if we perform additional CPT investigations. This has no effect on the transformation model uncertainty, but the measured property uncertainties associated with the CPT variability will reduce slightly. On scenarios 2 and 3, it says the same number, but it's more rounding area. There's a slight improvement. Now, what about if we did a rigorous site-specific hazard assessment? Well, again, it will have no effect on the transformation model uncertainties, but it does have a pretty similar effect on the measured property. We could also look at both. If we did both the additional CPT investigations and rigorous site-specific hazard assessment, here, now their combined effect reduces the measured property uncertainty and overall probability of failure a little bit more. But let's look at if we were able to do some high quality lab testing and use that to estimate liquefied residual strengths so that we didn't have to rely on the CPT-based transformation models. Finally, we'd see an effect on the transformation model uncertainty. And combined with the measured property uncertainty, these are the overall probabilities. And then lastly, we looked at the combined effect of everything together. And these are the final results. So, you know, what I said at the beginning is all case studies had the same factor of safety of 1.1. So if we used fully deterministic approaches, we'd have the same design decisions for each case study. But I think now potentially very different conclusions could be drawn when we also consider these probabilities of failure. For scenario 1, it seems like probabilities of failure are reasonably low for all scenarios. Of course, actual design decisions would have to depend on the risk profile of the facility, but you know, I think you could imagine scenarios where you might think that the liquefaction stability of the dam could be considered acceptable as is. For the second scenario, you know, you can see a clear jump there that indicates that performing lab testing has the potential to reduce uncertainty significantly, so probably worthwhile. And then in scenario 3, we see that the probabilities of failure are relatively high for all scenarios. You know, so looking at this, doing some additional investigations or lab testing doesn't really seem like it would provide any significant value in uncertainty reduction. So here, it may be time to just start thinking about improvement methods or buttressing. You can also step back again and look at how the different types of uncertainties contribute to the overall failure probabilities. So in this illustrative set of examples, the red portion that represents the transformation model uncertainties are almost always much greater than the blue ones that are representing the measured property. So, you know, a general clear pattern is that there seems to be limited benefit to doing additional CPT investigations or more rigorous seismic hazard assessments when your primary source of uncertainty is from the CPT empirical models themselves. So in these cases, instead, you know, incorporating a lab test-based program to calibrate the CPT results actually has the potential to reduce uncertainties significantly. So those are just some illustrative examples, but now let's move to something from the real world. These are tailings facilities that were closed about 15 to 20 years ago. And these photos are actually taken during the closure works, which included a great deal of stabilization, which included regrading and armoring the slopes of the tailings facilities. And those closure works were designed to meet industry best practice and stability criteria at the time. And since those closure activities, the facilities continue to be monitored and stability analyses are updated on a regular basis. Some recent site investigations included about 60 CPTs on the 5 tailings facilities there at the site. Here's just an example of one cross-section. The engineer of record here computed the factor of safety against liquefaction triggering using the CPT results and Idris and Bollinger's deterministic CPT relationship. And they actually made the decision to use 1.2 as a cutoff. So zones with factor of safety less than 1.2 were what was considered potentially liquefiable. And then so this is sort of a generalized interpreted cross-section of what they came up with based on those results. The bluish and reddish areas were the zones that were considered susceptible to liquefaction. They also use CPT methods to estimate liquefied residual strength ratios. In this particular case, they adopted Robertson's values in their stability analysis. And then those analyses showed that all facilities had post-seismic factors of safety below 1.1. So even though the facilities met best practice criteria when they were closed, there's now a concern that they don't meet current liquefaction stability requirements. A buttress was designed that would get to factors of safety above 1.1 or 1.2, and that buttress, was significant, had costs in the hundreds of millions of dollars. And it's also worth noting that this is a mining client that owns and operates a number of other tailings facilities around the world, some of which also might not meet current liquefaction stability requirements and may also require buttressing. So we were approached by them and they asked us to help them assess and understand their liquefaction risks, basically to help inform decisions that they need to make on the urgency and size of a buttress that might be needed. We decided to do a quantitative risk assessment or QRA to assess risks, and this could be a whole presentation on its own, but it's not the focus of today, so I'm just going to overview it at a very high level. The general process that we followed included identifying all the events, conditions, and hazard that could lead to a dam failure. We then converted those into fault trees, simplified fault trees to illustrate the failure sequence from initiating event to dam breach. And then we used event trees to represent the range of potential consequences that could occur following a dam breach scenario. I know that this is too small to see the details, so we can zoom into one of the branches and look at the simplified fault tree for seismic liquefaction as an example. So for this type of failure, we need the material to liquefy and then to have insufficient stability under those liquefied strengths. And the probability of liquefaction occurring depends on both the seismic event and the probability of liquefaction being triggered for that event. And these may seem familiar because they're essentially the same steps we talk about in the paper. So we can apply the paper methodology, but incorporating the site-specific information to calculate the probabilities for these different nodes. But this is just one dam failure mode. And we also have similar trees for all these other failure modes. And we included these other types of failure modes because even though the client raised liquefaction risks as the primary concern, we want to make sure that we don't ignore other risks that could be of equal or maybe even higher significance. And actually, some of the paper calculations, like those relating to uncertainty in the residual strength estimates and in estimating liquefaction triggering potential, can also be applied to these other failure modes too. And so now let's look at the results. The first results that I'm showing are the estimated probabilities of failure by failure mode. There are 5 TSFs at this site, but I'm just showing the results for one, basically because the overall patterns were pretty similar. This confirmed to us that the liquefaction and seismic failure modes were the dominant ones and the most important that were driving the risk. And then another common way to look at results of QRA is to plot them on these FN plots. So the N is the consequence in terms of number of fatalities, which is shown on the x-axis. The F is the frequency or annual probability of exceeding that consequence, which is shown on the y-axis. And one of the challenges with QRA or probabilistic approaches is that it's always hard to know what to compare to. So the different gray dashed lines on the chart represent a range of proposed tolerability thresholds, which can vary from different regions or jurisdictions. So here, with the white symbols, I'm showing the base case results for 2 of the TSFs in their current condition. So you can see the circle there, that plots just above all thresholds, whereas the diamond plots well below 2 of the thresholds and quite close to the 3rd. We also looked at the effect of the planned buttress, which, if we look at both of these, it reduces the risk for both facilities. For the circle, it goes from being above all tolerability thresholds to below 2 of them. And for the other facility, it shifts it down below even the negligible risk line. Let's look at these points a little bit closer. And one thing to note is that our estimates of risks are heavily influenced by uncertainties and factor of safety estimates. And a lot of those uncertainties relate to the underlying correlations or just limited data. And when we factored that in, we can see that this much that I'm showing on the slide of the difference can be attributed to uncertainties that are potentially reducible through things like additional investigations and test methods. And if we did those investigations and the results were favorable, they didn't show worse results than what we were expecting, then our revised estimates might actually land in the area shown by those dashed symbols. One thing to note, though, is that the dashed symbols sort of represent hypothetical best case outcomes. So really, another way to say that is that they show the potential value of additional investigation. So they shouldn't be, compared as directly to the more concrete results from buttressing. And, one other thing I think is important to emphasize is that, QRA results do not replace good engineering practice. Instead, I think they supplement it and help us make more risk-informed decisions. Like I said, at the beginning, based on factor of safety estimates alone, I think we would have said that all the facilities definitely need a buttress. But now, when you look at these results, you might decide, yes, a buttress is clearly worthwhile for this facility. But, maybe risks are acceptable as is for this one. as I've said a couple times now, so our estimated risks are heavily influenced by uncertainties, a lot of which comes from empirical correlations that have some built-in conservatism. And having unknown levels or layers of conservatism is completely acceptable for engineering design, but it becomes dangerous when you're trying to prioritize investment decisions, right? Especially, for a client like this, who's faced with making decisions about the need and urgency for buttressing across a number of sites. So the other thing is that these results also identified that there's potentially high value in performing additional investigations, not because they change the true underlying risks, but mainly because they may improve understanding enough to potentially reduce buttress size requirements, as an example. And the last thing I'll say about this is the client in this case did decide to do further work after this study. Some of these investigations are still underway, but some of the current findings are indicating that much smaller buttresses actually are likely to keep risks within acceptable levels. So now to wrap up, here are what I think are the key contributions of this work. First, it described the different sources of uncertainty in liquefaction assessments and how to quantify them. And it also demonstrated how the often ignored transformation model uncertainties can be quite significant. And I think this has a few implications. First, the implications for deterministic factor of safety-based approaches or estimates. I know you're probably already well aware of the many limitations of purely deterministic approaches. And I think this study simply pointed out another weakness of these methods, right? Sort of emphasizing, especially when they rely heavily on empirical correlations that have high uncertainties in their underlying transformation models. Next, implications for CPT uses. Actually, I want to pause here and make it very clear. I don't intend for this presentation to be a criticism of CPTs at all. I'm a big fan of CPTs and think they're obviously a very efficient screening tool and great at providing coverage for characterizing large areas. Instead, I think this paper is just trying to point out some of the big uncertainties underlying some key CPT correlations. And to recognize the risks of relying too heavily on them. Also want to show that there are a number of cases where a high quality lab testing program for calibration will actually provide much more value when the primary source of uncertainty is from those CPT transformation models themselves. And then lastly, implications for further work. I think we're always going to need to use empirical relationships, especially in the field that I primarily work in geotechnical engineering. But I think historically, the development of these relationships seems to have put a lot of focus on picking a perfect line location, like what's kind of shown in this example. Now, since we have more data already available, and as additional data becomes available and these empirical correlations get updated, I just really hope that further work puts much more emphasis on the uncertainty underlying the transformation models themselves, which I believe is much more important than arguing about slight variations as to where the line should sit. And just to conclude, as I said before, even though this is one specific example, these types of uncertainties apply to every parameter derived through empirical correlation methods, which I think are used widely across many areas of civil and seismic engineering. So I think now as we next move into the questions and discussion part of this webinar, I'd be very interested to hear from you and whether you see any parallels or relevance to your work. Thank you.
Thank you very much, Holly. Really interesting presentation. I think it's very educational in the way that you presented, and interesting cases that you showed. I see a lot of parallel on the work that I do every day. My field of work is mainly probabilistic seismic hazard assessment, where everything is about accounting for uncertainties and seeing how those uncertainties or additional data could help to better characterize the risk or the hazard in my case in specific. And actually one of, I would have one question. I would like to start with a question for me. Is in the cases that you were presenting, always if you add that data, you will reduce risk or you will reduce uncertainty. But that is not always the case. Sometimes we acquire more data and we realize that the case is even worse than we thought at the beginning. So that is kind of sometimes a bit of a hard sell for the clients, for our clients, is because there is always the expectation that if you collect more data, you are going to give them a good news and say, look, your uncertainty or your hazard or your risk is even lower than you expected. Sometimes it's just, it could be worse. And I think everything is about having a lot of the information required to take an informed decision. I don't know how you had faced similar situations in the work that you've done, and how you communicate that to the client.
You know, I think that's a very great point, and I'm glad that you brought it up. You know, I said I was trying to be careful in the presentation when I talked about it as framing it as the potential value of uncertainty reduction, which makes a big assumption that assumes as you get more information, you're just going to narrow those uncertainty bands. But as you've pointed out, there could be cases where the additional information actually shifts your estimates to something that was worse than where you were before. And those are cases. And I think, as you said, it all comes down to sort of to how do we communicate things, you know, deterministic approaches, whether something is a factor of safety of 1.5 or not, is simple, easy to understand, and a lot of people are used to it. Thinking about how we incorporate clear communication of probabilistic approaches and what they mean, and that there was still value in doing these investigations to be more confident about where we are and more confident in our ultimate design, even if it meant that, you know, some of our inputs got a little worse. I think it still leads to better designs overall. And I'm sorry, I think it's just something that is ongoing work and things to think about. And I don't have all the answers right now. I'd also be interested to hear how other people are doing that too.
Yeah, that is a very interesting topic, not only for one presentation, but I think it's the way how the community is going to those more probabilistic informed approaches. We have a couple of one comment and one question on the chat. So from Martin Lord, he says, really excellent presentation, thank you. So thank you, Holly. And then also we have from Brian Roman, he's asking, shall we move from a deterministic ELEM to a probabilistic approach when evaluating the stability of tailing dams? If so, what probability of failure would be acceptable for the post-earthquake condition?
Yeah, I think that's the second part of that question is a great question. I think that there's never any one silver bullet that solves all our problems. I think probabilistic approaches can complement deterministic approaches and vice versa. I actually think Suzanne Lacasse did her Rankine lecture in 2015, and I think a key theme of that lecture was about the need for both and how they complement each other in this industry. And I would defer to her comments on that, because I think she framed it very well in that kind of presentation on why they're needed for both. And one of the key challenges of fully probabilistic based approaches is that it's really hard to know what to compare the final results to, these probabilities of failure, and what's okay and what's not, which is directly what this question is asking. So, in the presentation, I showed that we have a bunch of tolerability thresholds that vary by region and jurisdiction. So there's not one acceptable answer for what probability of failure is acceptable. It obviously depends on the risk profile of the facility and the specific context.
Yeah, if I can add to your answer is, at the end of the day, I think we have to focus on risk, not necessarily on probability of failure, but what is the risk? I think all the decisions should be risk-based. So what are the consequences of such a structure failing? Yeah, the consequences are negligible. So probably you don't take into account only the cost of repairing and habilitating the facility back again. And in that case, you can afford having the high probabilities of failure. But if the consequences are high, for instance, on these tailing facilities, worldwide, we had very bad experiences of these kind of tailing facilities, of the tailing dams failing and provoking not only fatalities, but also ecological damage that could be quite significant and could last many, many years. So that, I think, has to be taken into account in the equation to understand, to take a decision of what is acceptable and what is not. And at the end of the day, probably also regulators have to take a view on that and define what is acceptable risk as well.
No, thank you. Yeah, very good points.
We have another comment from Andre Lima. He says, an outstanding presentation. He thanks you. Also from Joseph Mitimoa, great presentation, Holly. I wanted to ask if there is a chance for a graduate internship at SRK. So probably it's just, he needs to just contact you directly and or you want to answer that now?
No, I don't think, I think in case maybe you didn't hear at the beginning of the webinar, but I actually work at SRK Canada. It's probably better addressed by my African or Ghanaian colleagues, that one.
Yeah. I don't know if we have more questions from the attendees, but I will have one additional question as well. Have you ever tried to integrate this approach that you're developing with a PSHA in a way similar to what we do site response analysis, to do some sort of a convolution approach so you obtain hazard curves? In this case, should be hazard curves of the probability of liquefaction occurring. That would be a very interesting development.
Yeah, it's something that I'm actually actively working on right now for 2 different projects, and it's giving me an opportunity to work with colleagues and external people who are quite a bit more experienced on the probabilistic seismic hazard side, and yeah, I think they should be integrated together.
Yeah, and also another point, I feel I'm hijacking your presentation, but an interesting point as well is to start distinguishing in your methodology between what is the aleatory variability, what is intrinsically aleatory, and you wouldn't be by nature able to reduce even with more data, and what is epistemic. A very clear example in your presentation is the model-to-model variability. That is purely epistemic, and that is something that, as knowledge develops, we should be able to have better models and to have better transformation from, let's say, CPTs to soil parameters. But there are other characteristics that the soil, the nature of the soil is aleatory. So it doesn't matter sometimes. At some point, it doesn't matter if you have more data. You always have uncertainty on the parameters. So that's going to be an interesting thing to develop as well. We have another question from Jaime Castro. How will you define the risk threshold? Does the amount of information define the limit of tolerance as per alarm? I'm not sure you are familiar with alarm, but this term that is used here in the nuclear industry, that it should be proportionate to I don't remember exactly what it stands for, but it should be proportionate the amount of effort to the risk.
Yeah, I think the way that I commonly hear that acronym is as low as reasonably practicable.
Exactly. Yeah.
I'm not sure I understand Jaime's question about specifically how the amount of information defines the limit of tolerance, but I think in general, what I would say is, and very similar to Guillermo, your comments earlier, that just taking or following a risk-based decision process can lead to better decisions. And I think, applying probabilistic-based approaches feed into being able to do ALARP type assessments of risks, and when risks get to a point where they can be considered as low as reasonably practicable.
Yep. I don't see more questions. I know there are more questions. So Ali Kuram, he says, thanks for the nice presentation. Is it possible to consider earthquake uncertainty, it means record variability, separately from soil uncertainty?
Again, I'm not sure if I'm quite picking up the nuance of the question, but for sure the uncertainty related to earthquake sizes and characteristics is its own set of uncertainties, right? That is separate from the soil uncertainty that we account for, and interpretation of the seismic hazard is definitely its own set of uncertainties.
So another question we have from Amandine Bruce. Thank you for the presentation. To estimate the model uncertainties, did you statistically reanalyze the database on which the correlations are based? If yes, did you encounter any challenges?
So actually, Idris and Bollinger were quite kind, and in their latest update of their method actually quantified it. I did also statistically reanalyze it and got to the same answer, which added confidence in the approach. But I did have to do some statistical reanalysis of some of those residual strength transformation models. And in the Olson and Stark case, it's a simple regression line. I don't know, that process was quite simple. It wasn't particularly challenging.
I think we don't have more questions. So anything else you want to add, Holly, before I thank you for the presentation?
No, I don't think so. I guess thanks again for inviting me to do it in the first place, and thanks to everyone who stuck around on the call and listened to it. I think, Guillermo, you have my contact information there too. If anybody has additional insights or ideas and wants to chat, feel free to reach out.
Well, thanks to you for taking the time to prepare this very educational presentation. I think particularly the first slides, the introductions, I found them very insightful, very clear to explain uncertainties and how, for instance, one that I like in particular is how you show that the same factor of safety could result in different risk. It's not exactly, depends on the probability distribution that you have between the resistant forces and the acting forces. So I found it quite interesting. We have a good turnout for the second meetings. We are in a small society, so at some point we had 81 people connected to the call, so it's a good attendance. Thank you for everybody attending the presentation, and also congratulations, Holly, for the award on your paper. So, and thank you very much, and thank you everybody. Don't forget, next month, the last Wednesday of the month, we have another of the second evening meetings. So that is going to be a hybrid presentation. So we are going to be at the IC as usual, but also it's going to be broadcasted online. And the presentation is going to be on a new ground motion model for the UK that has been developed by John Douglas from the University of Strathclyde. So thank you, everybody. Thank you, Holly, and hope to see you around again.